All right. So I'm going to move on to small angle X-ray scattering. Just a real brief intro. I promise it won't take more than 5 minutes. And we'll move on to Mikkel's talk. You know, I give this part of the talk every year. We have the last version of this from the last Zoom conference at our YouTube channel, and plus a lot of tutorials that we've done at our YouTube channel and video. And the benefit of that is that you can hit 2 times the speed and listen to us in chipmunk mode and really absorb a lot of information fast. I like to start out with this picture of a water strider sitting on top of the water. And you can see that the 4 legs are in the water, and they're causing this sort of scattering of waves that are coming in. And of course, this guy just jumped down and created the waves, but what we're doing is more like we have a bunch of waves incident on this water strider. He's just sitting there. Actually, there's a little surfer here. You can imagine him being that. These waves are coming in, and they're interacting with the water strider or surfer. And then at the beach somewhere, you're measuring the difference between what it was like without the surfer or water strider in there versus when it was on a detector. So you're just watching how the waves have changed as a result. So that's the sort of basic idea of the experiment. You know, looking at a single molecule, the thing that we need in order to be perceived is there needs to be electron density, and in solution scattering, it also needs to be a different electron density from the water. If it's the same electron density as the water, you're not going to see anything. It becomes sort of invisible. So there's a, you know, electron density as a function of space. When you have that and you have the incident waves, so this is the electron density in space, then you have incident waves, and then you have your detector, which is measuring your intensity as a function of Q. And this Q thing, really, you can imagine that all of it depends on sort of the wavelength that's coming in, and that shape will change. By plotting it as intensity versus Q, regardless of the wavelength and sort of amplitude of these things, you're always going to get the same pattern. So that's what this Q thing does. Here is a nice slide that was generated by James Holton. He's calculating taking lysozyme, shooting an X-ray beam through it, and then looking at how the scattering pattern changes as it rotates around. So there's a lot of information in this particular image. And you know, when LCLS was coming on, this really freaked out the people who are thinking about doing single molecule experiments, because understanding all of this information is pretty tough, right? There's a lot of detail there. So that's a single molecule experiments. Looking also going all the way to the other side, doing crystallography. Let's say you have all these water striders and they're all perfectly aligned on a grid. Not only do you have the scattering from that single molecule, but you also have the order that's between the water striders. And you know, having many gives you a lot more signal than one. So that's great. That's one thing that's great about crystals, is that there's a lot of copies, and they're also organized relative to one another. And because of the relative spacing of these water striders, you get even bigger and more, you get spots on a grid related to where these are positioned. And you can see the sort of how the grid is in these HKLs. If you guys do crystallography, that comes in on top of the scattering formula, which I presented in the last slide. All right. Now in small angle X-ray scattering, you don't have the water striders or your molecules on a grid. They're all over the place. They're moving around in all orientations and averaged. And so relative to scanning profiles like this for crystallography, you lose a lot of information contents because of this disorder of the molecules. And you have to do some averaging. And these, you'll see a lot of triangular brackets. Those brackets mean that you're certainly averaging the information. So instead of nice, bright Spots, you're going to get rings, and those rings actually won't be tight rings like you would have in a powder pattern, but they're going to be more blobby rings. So that's SAXS. And there's a lot of information loss. You almost would think there'd be no information, but there is. This sort of setup still gives you information about how far apart these legs are from one another, and that's what this workshop's about, is how do you take that information and get to some kind of structural information. So just to review, from a single molecule, let's say DNA with 2 gold balls attached, you get a lot of information. You get sort of a scattering from 2 spots there, and that gives you a nice grid. If you were to take just tens of molecules, like 10 and freeze them all at once, you still get some of this information. And if you were to just take a quick snapshot, you get something like this. And then if you were to move them, allow them to move for a second, and then take a quick snapshot again, you get something like this and like this. So, you know, depending on the orientations, you would get a little less information than this, and each time it would be slightly different. With SAXS, where everything's moving all over the place, these profiles all get averaged, and you get sort of these more less detailed information, less fine images with less fine structure. And it's so much less fine structure that, in fact, you integrate rather than take these images. Like you might want to take these images in this case, but here we're just taking full 2D images to improve our signal to noise. If you take this line and integrate around it, you get the same as if over here. And we just kind of average through when we plot X-ray intensity versus Q. So that's what we're in the business of. I should mention that SAXS and SAS, which also includes neutron scattering and other scattering techniques, it's a difference technique, the way that we practice it. So we take like UV, a buffer, and a sample. We do that integration. The buffer is this black curve here. The buffer with sample in it is the red curve here. We subtract the 2 and we get our intensity versus Q. And that is the intro I wanted to give. I'll